When a carbonyl group is in conjugation with a carbon-carbon double bond, the resulting structure is called an alpha-beta unsaturated carbonyl compound. This is because relative to the carbonyl group, the alpha and beta carbons are unsaturated. They're linked by a carbon-carbon double bond. And these compounds are unique due to the electron withdrawing properties of the carbonyl group. They're electrophilic not just at the carbonyl carbon, but also at the beta carbon. And we can draw resonance structures to see this. So for example, we can start just by pushing the CO pi electrons up to oxygen to generate this classic O minus C plus resonance structure of the carbonyl group. But that positive charge looks allylic if you look at the carbon-carbon double bond next door. So we can continue to push electrons to illustrate that the beta carbon also has positive charge, is also sharing some positive charge character. And this means nucleophiles can attack both at the carbonyl carbon, and we've seen this type of electron flow many, many times before, or at the beta carbon. And this is new, and it's the subject of this video. When a nucleophile adds to the beta carbon, the result is called conjugate or 1,4 addition, and it's a great way to make carbon-carbon bonds, as we'll see, as well as other carbon heteroatom bonds if the nucleophile is heteroatomic, and a variety of nucleophiles can be made to add in a conjugate fashion. So we'll explore the structural and experimental factors that promote conjugate versus what we'll call direct or 1,2 addition, and learn how to engage conjugate additions in synthesis as well. So to begin exploring this, let's back up and think about conjugated dienes and draw an analogy between the reactivity of conjugated dienes and conjugated carbonyl compounds, alpha-beta unsaturated carbonyl compounds. When a conjugated diene like this, 1,3-butadiene as shown here, is protonated with an acid like HCl, the resulting cation is allylic and has two significant resonance forms in which positive charge is on the two ends of the allylic pi system here. The chloride ion can attack at either of those electrophilic positions, and the result is two isomeric products, one in which the chlorine has added, we might say, internally, and one in which the chlorine has added to the end carbon, in this particular case of 1,3-butadiene. One way we can look at this is through the lens of which atoms the H and the Cl ended up bonded to in each case. In the first case, H and Cl end up bonded to carbons 1 and 2, so we call this 1,2 addition. In the second case, if we think of the carbon to which H bonded as carbon 1, we see that the Cl is bonded to carbon 4. This is 1,4 addition, and this is what we'll refer to as conjugate addition in a carbonyl context when atom 1 is not a carbon, but an oxygen. And an important difference between this and what we'll see in a carbonyl context is the 1,4 addition product is an enol, and in the vast, vast majority of cases, that will tautomerize to form the keto form of that structure to give the final product. So the final product almost looks like 1,2 addition across two carbons, but we're going to keep in mind that tautomerization is often in play here. We can think of alpha-beta unsaturated carbonyl compounds as almost like alkoxide stabilized allylic cations, and in that sense they're electrophilic both at the carbonyl carbon and at the beta carbon. This leads to two types of nucleophilic additions, and we're going to look at these in more detail on this slide. The first is what we'll call 1,2 or direct addition, and this is the nucleophilic additions we've seen a gazillion times to this point in the course, where a nucleophile adds to the carbonyl carbon and the carbonyl oxygen is protonated, giving an OH group. This corresponds to a 1,2 addition. If we think of the carbonyl oxygen as atom 1, the carbonyl carbon is directly connected to it, that's atom 2. And keep in mind with these 1,2 additions that if the nucleophile is heteroatomic, nitrogen or oxygen, we may lose water here to form something like an imine, an enamine, an acetal, etc. 1,4 or conjugate addition is the other possibility, and this occurs when the nucleophile adds to the beta carbon. Notice that the beta carbon with respect to the carbonyl oxygen looks like atom 4. O1, here's carbon 2, carbon 3, carbon 4. So if we add an H to oxygen 1 and the nucleophile to carbon 4, this corresponds to 1,4 addition. And this may occur through an enol intermediate where this O is protonated, or an enolate where this O is an O minus. Under basic conditions involving organometallic reagents, for example, it's common for this to be an enolate, the conjugate base, essentially, of what's drawn here. Now, this won't stay this way, and this is an important difference to the reactions of butadienes that we looked at on the previous slide with HCl. This won't stay like this, right? This is an enol, and it will tautomerize either under the reaction conditions or upon workup to give a ketone in this particular case, the keto form rather than the enol form, right? And so the net result here, notice, is the addition of an H to the alpha carbon. There's one H here and ultimately two in the final product, and the nucleophile to the beta carbon. So we still call this 1,4 addition because an enol or enolate intermediate is almost certainly involved. What it looks like ultimately, though, is addition of H in the nucleophile across the alpha and beta carbons. This is known as conjugate addition commonly in the carbonyl context. Let's look now at some of the structural and experimental factors that dictate whether 1,2 or 1,4 addition can occur. And I should preface this by saying that in many cases, this can be very difficult to predict. There aren't really any simple rules here that we can use. There are a few simple rules, but rules are made to be broken in a context like this, and direct versus conjugate addition can be rather difficult to predict in practice. That said, we're going to look at 3 important questions that will allow us to make an educated guess about this, we might say. The first is about what we'll call the hardness or softness of the nucleophile, and qualitatively, roughly, this relates to reactivity. Hard nucleophiles have high charge density and are profoundly reactive. These are organometallic reagents like organolithiums and Grignard reagents, while soft nucleophiles contain stabilized and delocalized negative charge. These are things like stabilized enolates with multiple electron withdrawing groups stabilizing an anionic carbon. What tends to happen is these highly reactive hard nucleophiles tend to engage in 1,2 addition, while soft nucleophiles tend to engage in 1,4 addition. For nucleophiles that add reversibly, things like amines and cyanide, low temperature tends to encourage 1,2 addition, while high temperature tends to encourage 1,4 addition. The reasons for this are rather complicated, so I'll get to the details on that when we get to its dedicated slide. The Lewis acidity of the carbonyl carbon also plays a role. Highly acidic carbonyl carbons in things like acyl chlorides tend to promote 1,2 addition, while carbonyl carbons with low Lewis acidity, things like amides and to some extent esters, tend to promote 1,4 addition. And this, of course, depends on the nucleophile and the temperature as well. And so this gets a little complicated. It's wrapped up with the other factors, but it's something we should consider. The 2 reactions on this slide give you an example of the impact of the nucleophile. When the nucleophile is a Grignard reagent, this is a very hard, highly reactive nucleophile. Grignard reagents tend to add in a 1,2 fashion, and organolithiums are the same. They tend to add directly to the carbonyl carbon. Organocuprates are much less intrinsically reactive. They're much less intrinsically nucleophilic. These tend to give products of conjugate or 1,4 addition, where the R group is added to the beta carbon. And it's because these are in the category of soft nucleophiles. They're not as reactive, don't have as high negative charge density as the organolithiums and Grignard reagents. This slide brings us some clarity to this whole hard versus soft distinction and helps us realize why hard nucleophiles tend to add to the carbonyl carbon, while soft nucleophiles tend to add to the beta carbon. Hard nucleophiles have very high negative charge density in the R group. They tend to operate by what we might call charge control, where that negative charge wants to go to the carbon that has the greatest partial positive charge in the alpha-beta unsaturated carbonyl compound. And if you look at the partial charges in a typical alpha-beta unsaturated carbonyl compound, this one is acrolein with an aldehyde group directly linked to a carbon-carbon double bond. We see that the carbonyl carbon is definitely partially positive, and at least by my calculations, the beta carbon here is actually partially negative. So under charge control, nucleophiles will tend to want to add to the carbonyl carbon. And hard nucleophiles like organolithiums, Grignard reagents, and anionic nucleophiles like hydroxide and alkoxide will tend to want to add to that carbonyl carbon. Soft nucleophiles tend to operate through what we might call orbital control, where they're looking for the lowest unoccupied molecular orbital and where it has the highest orbital density or the largest lobes, more simply speaking. And if we look at the LUMO of this same unsaturated aldehyde, the largest lobe in the LUMO is actually on the beta carbon, and this is why soft nucleophiles like stabilized enolates, I should add the word stabilized here, as we'll see that enolates themselves are rather complicated, but stabilized enolates, enamines, arenes, if we're talking about Friedel-Crafts type reactivity, these will tend to add at the beta carbon where the LUMO density is largest. We have the largest lobe in the LUMO typically at that beta carbon. A large number of nucleophiles are what we might call borderline. These are nucleophiles that can add reversibly to carbonyl carbons, as we talked about in nucleophilic addition in the past. They're not obviously hard or soft, and they might add 1,2 or 1,4. The reaction temperature can actually be adjusted as an experimental variable to try to promote 1,2 versus 1,4 addition. And as an example, I wanted to consider methyl vinyl ketone as the electrophile and look at cyanide as the nucleophile, sort of classic borderline nucleophile here, cyanide or CN minus. At high temperature, we tend to get the 1,4 addition product with cyanide adding to the beta carbon. At low temperature, we tend to get the 1,2 addition product. The basic reason for this is that the 1,4 addition product retains the CO double bond, and so it's actually more stable than the 1,2 addition product where the CO double bond has been broken and we retain a CC double bond. But for reasons related to this charge distribution that we discussed earlier, the 1,2 addition product is often the kinetic product, the product that's formed more quickly. So at low temperature, we tend to see this come in first. If we allow the reaction to proceed to long reaction time or high temperature, we often see actually isomerization via equilibrium to the more stable 1,4 addition product, the thermodynamic product. The Lewis acidity of the carbonyl carbon, in particular, what type of group is connected to the carbonyl carbon, also plays a role in whether 1,2 or 1,4 addition can take place. Carbonyl compounds that have low Lewis acidity because they have a good electron donating group connected to the carbonyl carbon. Things like carboxylates, that's sort of the ultimate, with a negatively charged oxygen connected to the carbonyl carbon, or amides, where an electron donating nitrogen atom is connected to the carbonyl carbon. These are not very Lewis acidic at their carbonyl carbons, but because of the electron withdrawing effect of the carbonyl functional group, can still act as electrophiles at the beta carbon, and these will tend to engage in 1,4 addition. So for example, if we take this unsaturated amide and we hit it with sodium cyanide, the cyanide will add selectively to the beta carbon, and we'll see conjugate addition with essentially no reaction of this pretty happy carbonyl group, which is adjacent to an electron donating nitrogen atom. On the other hand, for highly Lewis acidic carbonyl compounds, we'll get reaction at the carbonyl carbon almost regardless of what the nucleophile is. So for example, if we hit this acyl chloride with sodium cyanide, we actually see substitution of cyanide for chloride, and this goes via a tetrahedral intermediate where cyanide is added to the carbonyl carbon, and then chloride gets kicked off in a beta elimination step, right? And in this case, this carbonyl carbon is so Lewis acidic that essentially we'll see no reaction of the beta position. Cyanide's going to add selectively to the carbonyl carbon, kick off chloride, and then we're essentially stuck at this substitution product.